All right, let's just jump right into it. Cosmic inflation. It's a huge deal in cosmology, right? A cornerstone of the Big Bang Theory. But what if the whole thing is built on a fundamental mathematical and logical error? Well, today we're going to break down an argument from physicist Miles Mathis, who claims exactly that the entire theory is based on a simple, yet pretty profound, definitional mistake.
And yeah, he does not pull any punches. I mean, this quote right here sets the tone from the get-go. He's comparing a pillar of modern physics to an old, unprovable philosophical debate. It's a really bold claim, and it frames his entire argument that the theory of inflation isn't just wrong, it's fundamentally unscientific.
So, where does a critique like this even begin? Well, Mathis starts not with inflation itself, but with the theories it's built on. His argument is, look, you can't have a solid theory if its own foundations are speculative, unproven, or, let's be honest, have already failed.
And this is his main metaphor. He sees inflation not as this sturdy pillar of cosmology, but as a house just teetering on unstable ground. He basically thinks the physics community is trying to put the roof on before they've even built the walls.
And this right here, this is the shaky ground he's talking about. He points out that grand unified theories, or GUTS, they've largely failed. String theory is, still totally speculative. Even the first big idea for what caused inflation, the Higgs field, that's been ruled out. And yet, he says, these are the very concepts that are still used to justify inflation theory.
Which brings us to this thing, the inflaton. This is the name they gave to the hypothetical particle or field that supposedly drove the whole process. Now, Mathis's definition here is, you can tell, intentionally dismissive. He calls it a ghost particle in a field of undefined ghost particles, just to highlight his view that it's basically a fudge factor, something invented to solve a problem without any real physical basis.
And this quote just perfectly sums up his whole point for this first section. Inflation is supposed to have happened at the end of the so-called grand unification epoch. But, as Mathis bluntly asks, if we don't even have a working theory of grand unification, how can we theorize about an epoch that's named for it? It's a classic case of putting the cart before the horse.
So after questioning the foundations, Mathis brings out what he calls his hammer of logic. And this is the absolute core of his argument. It's a critique that's not based on experimental data, but on the fundamental definitions of motion, space, and time themselves.
This is the one crucial question he claims all the top theorists just never stop to ask. The theory is literally called exponential inflation, but Mathis argues that if you actually look at the definitions, the very idea of an exponential expansion of space over time is a physical impossibility.
Okay, so here's his reasoning. Let's walk through it. He argues that any physical motion is either velocity, of simple ratio, right, distance over time, or its acceleration, which is really just a more complex ratio, like stacking velocities. The main point is that any real motion has to be what's called a power relationship, where time is the base. But an exponential relationship, that's a completely different mathematical animal. It isn't a ratio, and if it's not a ratio, Mathis claims it simply cannot describe a physical relationship between space and time, period.
This slide makes that distinction crystal clear. Look at the power relationship on the left, r equals t to the n. The variable, time, is the base. This, he says, is a ratio, and it's physically possible. But now look at the exponential relationship on the right, r equals a to the t. The variable, time, is now in the exponent. According to Mathis, you just can't get there from here. Space and time, he argues, simply cannot have that kind of relationship. So the bottom line is this: no matter how complex your acceleration gets, no matter how many velocities you stack on top of each other, you're always just building a more complex ratio. You will never, ever cross that mathematical line into a true exponential function. He argues that physicists are using the word exponential when what they really mean is just a crazy high-power acceleration, and he says that distinction is absolutely critical.
Okay, so what? Let's say we accept his argument that exponential inflation is impossible. What are the consequences? Well, the whole reason the theory was invented was to solve some really big problems with the standard Big Bang model. If inflation disappears, those problems, well, they come roaring back.
Let's just do a quick recap of what inflation was supposed to do. Back in the late 70s, cosmology had run into a few major roadblocks. And then in the 80s, inflation was proposed as this really elegant way to solve several of them all at once.
And these were the big three head-scratchers. You have the horizon problem, which asks why distant parts of the universe look so much alike if they never had time to communicate. Then the flatness problem asks why the universe's geometry is so perfectly balanced, and the magnetic monopole problem wonders why we don't see these weird particles that other theories predict should exist. Inflation kind of fixes everything. It smooths, it flattens, and it dilutes, seemingly solving all three.
And that's the real domino effect here. If Mathis's hammer of logic actually succeeds in demolishing inflation, then these foundational puzzles of cosmology are suddenly unsolved all over again. The explanations that physicists have been relying on for decades would just vanish, leaving a massive hole in the Big Bang Theory.
So in the last part of his paper, Mathis really zooms out. His critique, which started with just inflation, becomes this sweeping indictment of the entire way modern theoretical physics is done.
This quote just perfectly captures his final verdict. He believes physicists have gotten so obsessed with these grand abstract theories about the beginning of time that they've completely neglected to make sure their foundational knowledge, the walls and the foundation, is actually solid.
Now, this is a pretty provocative thing to say, but it's central to his conclusion. He argues that the whole field has started to incentivize selling these big, sexy, unproven ideas over doing the slow, rigorous work of actual science. The goal, he claims, has become publishing bestsellers and winning prizes, not discovering what's actually true.
And he really does not hold back. For Mathis, this alleged abandonment of basic logic isn't just some mistake. He calls it a sacrilege against the very principles of science. He sees it as an offense against rationality itself, like a field that has started trampling on its own gods.
And that kind of leaves us with this final thought. Mathis's argument, whether you agree with it or not, it forces us to look at the very language we use to describe the universe. It's a powerful reminder that sometimes the biggest revolutions in thinking don't come from some new discovery, but from just re-examining the definitions we've always taken for granted. So it makes you wonder, right? What other pillars of science might be resting on a simple, overlooked definitional flaw?